Okay, let's do another chi-square example instead of 2x2 table, which is where we were earlier. We're going to do a 3x2 table. The data from here are adapted. Let's call this yes and no. From the Stockberger reference, uses a quite unfortunate and dated, I think, example. So I'm going to make this one up. The data aren't made up, but the story is partisanship, Democratic, Republican, and other. That's in that's not an ordinal variable the way I have it set up. Illustrative too, that chi-square in the table doesn't require ordinal variables. It could be ordinal, nominal, ordinal, nominal, nominal. And here we have yes or no. Let's say yes or no to the question of whether or not climate change is a problem. 30 observations, very small data set. The frequencies, the observed frequencies are listed up here. 4, 2, and 3. 3, 16, and 2. Recall these are the column marginals. These are the row marginals, and we use those. Row marginal times column marginal divided by the sample size to find the expected FE, to find the expected value for each table, so for each cell in the table. So we choose this one. We want to know the expected value. It is 7 times 9 divided by 30. 7 times 9 divided by 30 is 2.1. 2.1. You have then everything that you need to calculate in this cell this little thing. FL minus FE squared divided by FE. The difference squared divided by 2.1. And in this particular case, it's a 1.72. Moving on here. Column marginal times row marginal is associated with this cell. 18 times 9 divided by 30. 18 times 9 divided by 30. In this case, is equal to 5.4. Don't want to put that there. 5.4 here is expected. And the overall calculation, FO minus FE squared divided by FE, is in this cell equal to 2.14. You've already done and you've already seen a chi-square problem. It was 2 by 2. This one's 2 by 3, and the significance of 2 by 3, more degrees of freedom. You're going to have a larger chi-square to say that this one's statistically significant, if you're willing to say that. But as you calculate this value across, you can get a sense already that this one is probably going to be statistically significant by the conventional standards that we make fun of. This one's going to be statistically significant. Recall in the other one, we had a 2 by 2, and we're only getting a value of 1 for each cell. In this case, we're getting 1.72 and 2.14. So chi-squared just, as we're summing across these two cells, is going to be north of 3. So let's move along. Neighbor has cranked up his lawnmower, which will greatly degrade our audio here. The expected value here is 5 times 9 divided by 30, and that's going to give you 1.5. You need to be doing this yourself. Going to have to do one on a test and quizzes too. So follow along. Check my work too, because I could get something wrong. This then, the whole calculation for this cell is 1.5. Moving along to the no category, 3. So here we have 7 times 9 divided by 30. That gives us 4.9. This calculation, then for this cell, is very small, actually. It's 0.74. And next to last, 18 times 21 divided by 30 is going to give you 12.6. 16 minus 12.6 squared divided by 12.6, which again is this, is going to be very small also, 0.92. Getting smaller ones down here, but it's still going to be enough, especially because of this. So the expectation here is 5 times 21 divided by 30, and that would be 3.5. 2 minus 3.5 squared divided by very small 3.5 gives you 2.25. You now have everything you need. The only thing you need to do is sum. Don't think you can see that. Sum across the cells. The answer to the chi-square problem here is 7.66. 7.66, and its p-value is, I have here for 2 degrees of freedom, reminding you the degrees of freedom was number of rows minus 1 times number of columns minus 1, and we have 2 rows and 3 columns, so 2 minus 1 times 3 minus 1 is 1 times 2, so the degrees of freedom here are 2. This is what I've listed up here. 7.66 you can see is larger than the critical value associated with 0.05, so you would say you're 95% confident. I prefer to say that we're less than 5% uncertain, but the norm is to say you're greater than 95% certainty that there is a relationship here, that these two variables are not independent, and we have, I found 0.00022 is the exact p-value that's spit out by the computers. You don't have to reference a table or anything. I do want you to know how to physically calculate this and finish this section with just a couple of brief comments. We established with this 7.66 and the 0.022, so it's really close to 98% confidence, right? That something's going on in here. What chi-square doesn't do, and we'll see in coming videos some tools that help us to better understand this, what chi-square doesn't do is say anything about the nature of the relationship. So these things are not independent. They're not independent, and yet we can't say really anything else about them. We can't say if one goes up, the other goes down, or just from staring at the crosstab with all of this mess in it, you can't see anything about the nature of the relationship between these two. We're going to move in coming videos toward understanding tools that do more than just test for jumping through the first hoop of causal inference, saying that two things aren't related, to examining tools and then visualization in class, examining tools that help us get a handle on how things are related. And ideally, that would have been driven from the very beginning in your research by theory, and yet things are what they are. So that's it. Another example. You could do a 3x3 crosstab. Instead of 2 degrees of freedom, you would have 3, right? 4, excuse me. And that's it. So practice on this, and again in class we're going to be doing this using R and real data sets. Moving on.